Good morning, everyone. I'm AAS Press Officer Rick Fienberg, and I'm very happy to see a room full of people attending the 231st AAS meeting here or near Washington, D.C. We're actually in National Harbor, Maryland. I'm assisted today by my two longtime deputy press officers, Inga Heyer and Larry Marshall. They'll be monitoring the webcast and helping out during the Q&A. I want to remind everybody to silence your cell phones. I just checked mine. Mine has gone off in a past briefing, which was extremely embarrassing. A press release just went out from the Sofia project to the AAS press list, so look for that if you haven't seen it yet. And so the way these work, if this is your first AAS press conference, is that I will make a brief introduction and let you know who all the presenters are. Then I'll turn it over to the first presenter. They'll all give their talks, one right after the other. We'll hold the Q&A for the end. So I'll come back up at the end and we'll do the Q&A, and we'll alternate between here in the room and for the people who are tuned into the Q&A chat on the webcast. I want to make one announcement for the press corps. Please remember that we do have a press reception this evening hosted by the National Radio Astronomy Observatory, an opportunity to meet the NRAO director and hear about some plans for the future of the Very Large Array. All right, so the press conference this morning is themed Astronomy from the Stratosphere, and we're going to hear a bunch of results from the Sofia Airborne Observatory. That's the Stratospheric Observatory for Infrared Astronomy. It's one of my favorite projects in astronomy for two reasons. One, I did my degree in infrared astronomy, and two, I have flown on Sofia, and it's a gas. And if you're a journalist and you can get an assignment to do a story about flying on Sofia, you too can fly on Sofia. So we're going to hear 4 presentations plus a little bit of background. The presenters this morning are Kimberly Ennico from NASA Ames Research Center. She's going to give us an overview and introduction. Then we're going to hear from Enrique Lopez Rodriguez from USRA and the Sofia Science Center, talking on Sofia HAWC+ polarization in galaxies. It's all about the magnetic fields. Elizabeth Tarantino, we changed the order a little bit. Next is going to be Fabio Santos from Northwestern University, talking on HAWC Sofia observations of the Rho Ophiuchi A star-forming region. And then B.G. Andersson, also from USRA Sofia, will talk about interstellar dust grain alignment. Why do we detect polarization, and what does it mean? And then finally, Elizabeth Tarantino from the University of Maryland will talk about characterizing the origin of ionized-carbon emission from spiral galaxies. Now, a lot of these topics sound kind of esoteric, but if you look at the press release, you'll discover that there's actually quite a bit of very interesting stuff going on here. So with that, I'm going to turn it over to Kimberly, and we will go right to the presentations. So you can just hit that one when you're ready to.
Okay, thank you. Good morning, and thank you for attending the press conference on Astronomy from the Stratosphere. I'm excited to share with you recent results from our flying observatory. Sofia has a Hubble-sized telescope in the belly of a 747 aircraft. It is a unique facility. It has a very vast instrument suite that will enable studies of a variety of phenomena. And by being an airborne telescope, you get above 99% of the Earth's water vapor. This reveals the infrared universe. Sofia embarks on doing a wide range of science investigations, from the study of planetary atmospheres and comets, to the formation of stars and planets, to the role and properties of gas and dust in evolved stars, the interstellar medium, that's the stuff between the stars, interstellar medium in our galaxy and in other galaxies. This is all made possible because our facility has the ability to renew our instrumentation. So today we're showing you 4 results. 3 of them are featuring our latest instrument, the HAWC camera. The HAWC camera is a far infrared, covers 50 to 200 microns in the infrared universe, plus a polarimetric capability. And we're sharing these new results from our community. The first speakers, the 3 speakers, Enrique will talk about the role of magnetic fields and how they play in galaxies. And next we'll hear from Fabio, who will share with us detecting an interstellar magnetic field. BG will round out the HAWC results by putting a little bit of emphasis on using Sofia to test theory, because we finally have an instrument that is delivering observational evidence to give theorists something to chew on. And we close with Liz. Liz is going to show a result on star formation using another instrument on Sofia, the German-built GREAT instrument. It's a high-resolution spectrometer, which was measuring the ionized-carbon line at 158 microns, showing how gas cools to form clouds. So I'm very excited to introduce these users of the Sofia Observatory and some of our latest results. So I'm going to hand it over to Enrique Lopez Rodriguez from the Sofia Science Center at NASA Ames in Northern California.
Okay, so today I'm going to talk about the magnetic fields in galaxies, and I'm going to show the first results of far-infrared polarimetry in stellar galaxies using HAWC+. First of all, okay, so we know that galaxies are formed by stars, dust, gas, and dark matter, and we know that in small scales, stars are formed by a gravitational collapse of matter, but we also know that without the magnetic fields, stars cannot form. Also, we know that without the magnetic fields, the interstellar medium has some specific properties. We know that magnetic fields play an important role in the dynamical evolution of this interstellar medium within the galaxy. This is the small scales inside of the galaxy. However, we know little about what is the structure and morphology of the magnetic field at galactic scales. And here is what I want to focus on, like what is the geometry of these large-scale magnetic fields, and if there is some specific large-scale magnetic field, and also if we observe one, what is the dominant physical mechanism of the large magnetic field in galaxies. However, magnetic fields are complicated to study, to observe, because we cannot observe magnetic fields directly. We need to observe the effect of the magnetic field in the matter in the galaxies. So now we have an instrument that is able to observe the effect of the dust in galaxies specifically. So we have a HAWC+ in Sofia, which is work on between the 50 to 250 microns. As I show there on the right side, you have the suite of instruments in Sofia, and you have the spectral range of HAWC, which is above, so beyond the spectral range of the James Webb Telescope, which is so HAWC+ show a unique spectral range that is not accessible by any current space-based telescope, so any space telescope in the near future, in 15 or 20 years from now. So not only is the spectral range, but also is showing a new, so is offering a new observing mode, which is the polarimetry mode. So because it's working in this spectral range of 50 to 200 microns, 250 microns, it samples different dust temperatures between 10 kelvins to 100 kelvins, which allow us to study different temperatures and different gradients of temperatures in the galaxies. So we have a few things. So we have a different spectral range, and also we have the high spatial resolution of a 2.5 meter telescope in the spectral range of 50 to 250 microns. And also we have the polarized capability of HAWC+. So I'm talking about polarization and how can we infer magnetic fields with this observation. So I show here a very basic idea how can we estimate magnetic fields. Later on, B.G. Andersson will go in the detail. So the idea here is, so we have dust in the interstellar medium, And we know that if it's no magnetic fields, so we have randomly oriented dust grains in the interstellar medium. If there is some magnetic field, then that will make the dust grains align in some specific orientation. And that is what we are observing here. We are observing the emission from aligned dust grains by a large-scale magnetic field. So the scale, the magnetic field that I show here is these black lines with the B, with the capital B on top, and this is the lines that we want to infer from the polarized emission observed by HAWC+. So after this technical view of the polarization, I show the results. So here, what I show is the first results of the polarized far-infrared emission in a external galaxy. What I show is the following. So this is the galaxy M82. It's known by a very strong star formation region in the center of the galaxy. So you see the color scale represents the emission or the thermal emission of dust at 53 microns, and the lines that you see on top represent the orientation of the magnetic field. So you see the galaxy is oriented at around 45 degrees with a disk in the center dominated by star formation, but we see some magnetic fields which are perpendicular to the disk plane. And also, not only the magnetic fields not only are the size of the galaxy, it also goes beyond the galaxy in the bipolar direction, that go and is enriching the intergalactic medium with dust and gas that is being pushing out from the star formation region in the center of the galaxy. The other galaxy that we observed was NGC 1068. This is a very famous galaxy that contains a supermassive black hole in the center and a accretion disk, and also a jet that is pushing away matter from the center. And this active galactic nuclei is inside of a massive spiral galaxy, which has an unusual high star formation rate in the spiral arms. As I showed before in M82, in this case, NGC 1068 is a face-on galaxy. The color scale represents the emission of dust, and these lines that I show there, that looks like a spiral arms. This is the magnetic arms due to the polarized emission from aligned dust grains in a magnetic field that is the scale of the galactic, of the host galaxy. So we have here two different galaxies. One of them is H-on, where we have outflows, bipolar outflow that is pushing away matter outside of the galactic plane and enriching the composition of the galactic medium. And in the other case, in 1068, we have a magnetic field that is confined in the galactic plane and is making the gas and dust flowing through the spiral arms due to the dominance of the magnetic field in the galaxy. So just to finish, so what we did here is we did the first far-infrared parametric observations of external galaxies using HAWC+, which allow us to map the whole galaxy and has enough sensitivity to obtain these parametric observations. So we found larger scale magnetic fields in both of the galaxies, and it's due to polarized emission from a globally large-scale magnetic field that is aligning dust grains in the galaxy itself, and also outside of the galaxy in the case of M82. So what we learned? So we learned that in the case of M82, the starbars, the star formation in the center of the galaxy, is strong enough that it's pushing away all the dust and gas outside of the disk of the galaxy, and also drawing the magnetic fields in the center of the galaxy to pushing them outside in a bipolar outflow. In the case of 1068, we have a galactic plane magnetic field that dominates the disk rotation in this galaxy. And now, so I would like to continue the press conference with Fabio Santos from Northwestern University.
Hello, everyone. So my name is Fabio Santos. I'm a postdoc at Northwestern University. I'm also part of the team that developed HAWC+, the new far-infrared polarimeter for Sofia. And I'm going to be talking briefly now a little bit about star formation. Okay, so just to point out that Enrique was talking about things on the scale of entire galaxies, but now we're going one size scale below that, and we're going to be looking at things inside the galaxy. So we're going to be focusing on specific interstellar clouds. So understanding how stars and planets are formed is one of the greatest challenges of modern astronomy. This is something that many astronomers have been trying to do for many decades, and as a matter of fact, this is one of the key science topics for the HAWC+ project. We know, the basic idea is that we know that stars and planets are formed inside large clouds of molecular gas and dust that exist basically in the plane of the Milky Way galaxy. The image here that you see to the left, this is a beautiful image of the main focus of this work. This is from Spitzer, and this is the Ophiuchi molecular cloud. You can see these beautiful patches of gas and dust, and several stars are forming in there. Okay, so the basic idea is that these big clouds, they tend to contract under their own gravity, and then these clouds, they become denser, they fragment into clumps and denser cores, and inside these dense cores we'll find these baby stars. Okay, so it's a very complicated process that, as I said, many people are trying to understand for several years. And to make things even more complicated, we know that our galaxy is filled with this huge network of magnetic field lines. So this is what this image to the right is showing. These are observations of magnetic field in our galaxy from the Planck Space Telescope. So it is believed that these magnetic fields could impact on how these clouds contract and form stars. And they could have an impact, for example, on how quickly the stars are formed, what are their masses, what is some properties of the planetary disks. So if we really want to understand star formation, we must observe and understand magnetic fields in our galaxy as well. And one way we can do this is through observations of the interstellar polarization, as Enrique was discussing, okay? So in this particular work, we're focusing on the central parts of Ophiuchi. This is called A. And this is a key target for the HAWC+ project because it's one of the closest star-forming regions to us. So this means that we can distinguish the details of the cloud structure very well and the magnetic field structure very well. This cloud is actively forming hundreds of young stars, and many of those stars will probably become stars like our sun with planetary systems as well. So HAWC+ was designed to map these magnetic fields in these clouds through interstellar polarization. And with polarization, we are basically looking at the orientation of the oscillation of electromagnetic fields from the thermal emission that comes from these clouds, okay? And I should emphasize that Sofia is currently the only project that is able to map magnetic fields in this particular part of the spectrum. So this type of science that I'm just going to present now can only be done with Sofia, okay? So this image that you see here to the left, this is a polarization map of the center of Ophiuchi. Each of those small lines is an individual polarization detection. And what happens is that these dust particles that are inside the cloud, they emit thermally, But in addition, these dust particles, they tend to be elongated and aligned with respect to the magnetic field lines, so that when we detect this thermal emission, we notice that it is slightly polarized. So we can use this polarization to trace the structure of magnetic fields. This is what is being shown here by this visualization of magnetic field structure at the center. So this is interesting. However, one piece of the puzzle that is missing is that if we want to convert from observations of interstellar polarization and interpret magnetic fields, we must understand how these grains become aligned in the first place, okay? So this is the focus of this work. We're trying to test one of the most promising grain alignment theories, and we're doing that by looking at a property called the polarization spectrum, which basically means that we're looking at polarization in different wavelengths, okay? So this map that you're seeing here, this was done in one wavelength, but we also observed the same part of the sky in another wavelength. So we're combining these two wavelengths and testing what happens to the spectrum. So this grain alignment theory, it actually makes predictions about how the spectrum should look like, and we can test these predictions with Sofia and HAWC+, okay? So the image, the colorful image that you see here at the center, this is the main result of this work. What this means, this is a map of the ratio between, of polarization between two different wavelengths. And you can interpret this as a map that shows the differences in the slope of the spectrum across the cloud, okay? And you can also see that in that images there are some lines, and those are contours that are showing where the cloud is dense, okay? So one thing that we notice right away is that when you go from the more diffuse areas of the cloud to the left into the denser parts of the cloud to the right, the colors in the image change. And what this means is that the slope of the polarization spectrum is changing as we go into the clouds. And this is exactly what is shown by this graph here to the right. These are quantities that represent the slope of the polarization spectrum and the cloud density. And there is a pretty interesting correlation between them, okay? And it turns out that this change in the polarization spectrum is consistent with the grain alignment theory known as radiative torques. So in the next talk, BG will give more details about this physical mechanism, but in general terms, what this alignment mechanism tells us is that the interstellar grains, they need radiation in order to align efficiently. So it is expected that the grains that are in the outskirts of the clouds, they receive more radiation, so they should be better aligned. So as you go into the clouds, you start going into very dark places, and then the grains receive less radiation, and then they are not very well aligned anymore. So a consequence of that is the change in the slope of the polarization spectrum. So this is what we believe that we're seeing here. So just a few final remarks. This is the first clear observation of systematic variations of the far infrared polarization spectrum within an interstellar cloud. And these changes, they are consistent with the radiative torques grain alignment theory. So this is an important result because it puts us in a more solid grounds in order to study magnetic fields and what's the role of magnetic fields in star formation, okay? So thank you very much. This is what I have. The next speaker will be B.G. Andersson from the Sofia Science Center.
So thank you, Fabio, and good morning. So as soon as we get this thing launched, there we go. I'd like to talk a little bit this morning with you about why it is and when it is that we can't interpret the polarization we see as magnetic fields. So interstellar polarization in the optical was discovered almost 70 years ago. And in the far infrared and emission polarimetry in 1982. Already a couple of years after Hall and Hilter discovered polarization, there was a theory proposed that explained or intended to explain why we saw this polarization. However, it had the disadvantage of having very few testable predictions coming with it, except beyond saying, well, here we go, we get polarization from dust. So we do know that in general, when we see polarization, whether in the optical or in the far infrared, it comes from elongated dust grains aligned with the magnetic field. So usually, it's safe to say that we're looking at magnetic field when we're interpreting a polarization map. But it actually isn't always true. And so we have to understand the microphysics of how this alignment happens to really know which magnetic fields we're looking at and what it means that we see that. And we have been testing this for a number of years now, and I want to show you some of those results. So to give you a little bit of a cartoonish explanation of what the problem is here, if you take an elongated dust grain in the interstellar medium and you give it a kick, it will start rotating, but it will typically rotate about some arbitrary axis. And here in the poor man's animation, if you rotate the grain about this axis, its projection to you will be time variable and therefore will not produce a polarization signal. So the first thing we have to do is we have to somehow make the grain rotate around one of its principal axes, and therefore that individual grain will give us a fixed projection on the sky. Now, of course, that's only good for one grain, and we can't measure individual grains. So in addition, we then have to figure out how we get all these grains that are nicely, it's called internally aligned, to go from this state where you see just a jumble to this state, which is the one that we all use when we show illustrations of why we see polarization. So the question is, how does this happen? So as I said, the Davis-Greenstein theory, as it's called, that was proposed in the early 50s, had very few specific tests that could be made on it. But somewhere in the mid to late 90s, there started to be a number of observations and theories that were raising concerns. And there was actually an almost Kuhnian scientific revolution that happened, such that in that time and up in the next decade or so, this new theory that Fabio was talking about was developed primarily by Bruce Drain at Princeton and Alex Azarian at Wisconsin. So it's known as the radiative alignment torque theory. And it predicts fundamentally that if you shine light on a dust grain, then it will start spinning in a mechanism quite similar to the little wind spinner that you can see at party stores and county fairs and stuff like that. Now, if the material of the dust grain has the characteristics that the silicate grains or the sand grains have, then that rotation will make the dust grains susceptible to magnetic field, and the interaction will then line up the dust grains with the magnetic field. One of the things I'm going to be talking about in a minute here is the fact that the other main component of interstellar dust, the carbon grains, or the soot, if you wish, does not have the solid state material characteristic that will respond to magnetic fields. So carbon grains in rat alignment should not be aligned. And so the point, besides being able to address a 70-year-old conundrum here, is both that if we can really nail down the parameters of rat alignment, both in terms of its conformation and in terms of its detailed quantitative parameters, we may be able to better understand magnetic field and to form and get new probes of the interstellar medium and the dust. And so we are presenting two new tests of rat alignment this week. The first one, which is a poster by Ilya Medan, who sits back there in the back row, if you want to talk to him, is a poster in which we ask the question, can we show directly that the amount of alignment or amount of polarization is driven by the radiation field? So what we did here is we used the wall of the local bubble as a screen against which to measure alignment. So the local bubble is a low density cavity surrounding the sun that probably was blown by hot star winds and supernovae over the last many million years. But that has the advantage that all the dust is at the distance that we understand where it is, and we know where the radiation sources are. So on the left-hand figure here, the red contour is the wall of the local bubble. The gray spots or the gray blobs are the location of the nearby OB associations, which shine light on the local bubble. And indeed, what Ilya is able to show is that the grain alignment efficiency is directly coupled to the amount of light that you get from these OB associations. So when you, from the sun's position, when you walk your way around the local bubble around us, the amount of polarization you see directly corresponds to where the OB associations are. The other experiment we are presenting here is to address the question of the mineralogy of the dust grains. In other words, can radiation align the carbon grains? So as I said, in order for the dust to align with the magnetic field, you have to have dust grains that have the characteristic of being paramagnetic, but which the silicates or the sands are. The carbon grains, again, are diamagnetic, so they don't interact with the magnetic field. But rat alignment tells us that if you have a strong enough radiation field with a strong enough directionality, instead of lining up along the magnetic field, the grains are going to line up along the radiation field direction. So, in other words, if we want to test the alignment of carbon grains, what we want to do is we want to find an environment where they're not swamped by the alignment and polarization from the silicate grains, and preferably also a place where we have a strong radiation source that's very localized, i.e. a star. And the best place to do this, we have found, is to use the circumstellar envelope of the carbon-rich asymptotic giant branch star IRC 10-16, which Eric Becklin will tell you about the discovery of at his Russell lectureship on Thursday. So this is a kind of star that's very old. It's about to become a planetary nebula. It has blown a large, very dusty shell around itself. And so it's ideal for measuring, for testing carbon grain alignment with the radiation field. And down to the left, down to the right here, you see the result we got. And you see a very symmetric, highly radial polarization field around the star. It turns out this polarization is directly correlated with the temperature of the dust. So both the temperature and the polarization is driven by the radiation from the star. And so we are confident that this is radiative alignment of carbon grains. And so it also supports rat alignment. And before I yield the podium back to Kimberly, I just want to make sure we take the opportunity to also thank Darren Dowell and Al Harper, who originated and built this fantastic instrument. And with that, I'm going to leave it back to Kimberly here. Oh, sorry. Of course. Elizabeth Tarantino from Maryland. Sorry, Liz.
Liz is long hair, actually.
Hello, everyone. My name is Elizabeth Tarantino. I'm a second-year graduate student at the University of Maryland, and today I'm going to be telling you about the ionized-carbon emission from two spiral galaxies. So the three previous talks that we just saw were all about star formation, but they were focusing on the polarization and the magnetic fields that affect the process of star formation. What I'm studying is how exactly we get gas to cool to form the stars that we see today. The large pictures, we start out with large clouds of neutral gas that are not very dense, pretty tenuous, and then those need to cool down and contract into molecular clouds, such as the famous pillars of creation that you can see in the center there. Then the molecular clouds also need to contract even further and cool to form the stars that we see today. So one of the major questions in astronomy today is the details of how we get this gas to cool. And one way that we get this gas to cool is through ionized carbon emission at 158 microns. This is the most important coolant for a neutral molecular gas at these intermediate densities before they really start to condense down into these stars. So the 158 micron is a far infrared line. It's a fine structure line, and it's one of the brightest far infrared lines in galaxies. It's used as a tracer of star formation in nearby galaxies and also galaxies that are very far away. But the interesting thing about C+ emission is it can be seen in 3 different phases of the ISM. So you can see it in the molecular gas, which are areas that are actively forming stars. You can see it in the neutral atomic gas that are at the more moderate densities. And you can also see it in ionized gas around massive stars. So one of the big questions that we're trying to answer is what is the contribution of each of these different phases to the total C+ emission in nearby galaxies? And this will contribute to how C+ is cooling down each of these phases to produce the stars that we see today. We're also wondering if this depends on the local environment of the region. So I want to discuss the importance of Sofia for this work. So C+ emission is a far infrared line, which means that we need to be in the stratosphere, above all the water lines in order to see it. Additionally, Sofia excels at high spectral resolution observations. Previous observatories, such as Herschel, that were space-based, weren't sensitive enough at these resolutions and at this line in order to really make detailed observations of this. And it's important in order to determine the origin of the ionized carbon emission to have very highly resolved spectral observations. So the GREAT spectrometer on board Sofia, you can see it right there to the right, is the only instrument that is capable of making these measurements at extragalactic distances. So here's a picture of the 2 galaxies that we observed and the different regions that we looked at with the Sofia GREAT spectrometer. The color right there is the Spitzer warm dust emission, and it also traces star formation. So we received 77 spectra from GREAT among these 2 galaxies, M101 and NG6946. These are both face-on galaxies and nearby, about 20 million light years away. And we chose regions that span different environments, ones that were interarm, which have less star formation, and ones that are star forming, which have a lot higher star formation rates. We then took a look at the spectra, and we compared the spectra that we received from the ionized carbon with that of the molecular gas and the neutral gas. So the ionized carbon emission from Sofia is in the blue right there. And then the molecular gas is in the red, and the neutral gas is in the green. So what we did is we found the combination of atomic gas and molecular gas that best reproduce the C+ spectrum. So you can see that the C+ spectrum kind of looks like it's in between the molecular and the neutral gas, meaning that it's coming from both of these regions of the ISM. So for this example region, the data are consistent with around 60% of the emission coming from the atomic gas and 40% coming from the molecular gas. We then can repeat this analysis for all of the regions in our galaxies. And what we find is this, where the C+ association fraction is on the x-axis, and the star formation rate for the specific region is on the x-axis. And what we find is 2 different regions come out. One where the atomic gas dominates and one where the molecular gas dominates. So there appears to be a transition that's associated with star formation rate. So where stars are more actively forming, the cooling of molecular gas in C+ emission dominates. Where they are not, C+ mostly is cooling the atomic gas. And as you get to higher star formation rates, we believe that ionized gas may begin to contribute. And we're working on quantifying that ionized gas contribution as well. So in summary, studying this ionized carbon emission can help us uncover how gas cools to form the stars that we know, and also can help us interpret the C+ emission, which is this very bright line that we can see in galaxies far away. With Sofia and the GREAT instrument, we're able to actually study this, unlike previous instruments, and we tentatively see this association with atomic gas at low star formation rates. Thank you very much, and if you have any questions, feel free to attend my session today at 2 p.m. Now I'm going to give it back, and we're going to do questions as a whole.
That's right. So in closing, to round up what you just heard, NASA's goals in astrophysics are to discover how the universe works, to explore how it began and evolved, and to search for life on planets around other stars. This morning you've heard how Sofia is helping us discover how our universe works. The role of magnetic fields in star formation and channeling flows in galaxies is still today one of today's unanswered astrophysics questions. And Sofia, our infrared observatory, is providing valuable insight into this question that no previous facility has addressed, nor will it be addressed with James Webb and WFIRST. You heard from Fabio Santos, who showed us the first time seeing variations in polarized light with wavelength within an interstellar cloud. Are we detecting an interstellar magnetic field? Enrique Lopez Rodriguez showed us examples of magnetic fields on the galactic scale, and in particular, really revealing a magnetic arm along the spiral arm in an AGN, NGC 1068. Now, is this common? If so, what does this mean? With these initial results from the new instrument on Sofia, opening up the field of looking at magnetic fields in a variety of objects, the interpretation of this data are dependent on the supportive theory. B.G. Andersson walked you through an example that we're using Sofia also to do direct tests of theory. Theory predictions, whether or not we are understanding how our universe works. And Liz rounded up the discussion addressing astrophysics questions that are still unanswered on how does gas cool down to form clouds and then eventually stars, looking at the ionized carbon line at 158 micron, only accessible by Sofia today. Figuring out where this emission comes from is vital to understanding. So here there's the numbers of the different presentations, oral presentations later today and throughout the week. Sofia discovering how the universe works. And I'm going to hand it over to Rick, who will coordinate the Q&A sessions. Please feel free to also talk with me and the other presenters here, and stop by the Sofia booth, number 515. We have a lot more science to show. Thank you.
All right, thank you all very much. So if you're in the room and you have a question, please raise your hand and then wait for the microphone. And when you get the mic, please identify yourself and who you write for. And then if you are on the webcast, please queue up your questions through the chat, and Inga will relay them here in the room. So we'll start with questions here in the room. Okay, we'll start down here. Larry, do you have a mic? Yeah, there should be two.
I'm David Aronstein from the American Physical Society. My question is about the first talk, the magnetic fields of the galaxy. Could you say precisely what is the novelty? What specifically, I'm looking at this pretty image of magnetic fields on a galaxy. So tell me what exactly has not been seen before. I think it's been said a couple times, and I just want to make sure I have it clear about what has not been seen before about magnetic fields in a galaxy. And I guess related to that is there still some uncertainty about whether you actually do have the magnetic field nailed down, or is there still some theory to work out on that? Thank you.
We're controlling the mics from the back. We don't need to push the buttons up here, do we, Nick? No, you
No.
guys shouldn't worry about the buttons. Nick's
Okay.
controlling it. Yeah, we
Okay.
got you. We got you.
The second question, like if we know if it's magnetic fields or no, I think that VG already said that we cannot specifically believe 100% that it's magnetic fields. There is some ideas on like if it's, for example, M82, if it's dominated by radiation pressure of the outflows, or it really magnetic fields dominated. So at least in M82, we need to specifically try to distinguish between radiative pressure because of the outflows, or is some really high, large-scale magnetic fields. In the case of 1068, these spiral arms has been observed before in the optical, but the optical are dominated by scattering processes. So here what we are seeing specifically is dust grains in the spiral arms that we know that is dominated by dust emission, and we know that we will not observe any homogeneous or large-scale spiral arms in the far infrared if it's not dominated by magnetic fields. So in the case of 1068, we can say that it's dominated by magnetic fields. In the case of M82, we need to study between what is the radiative pressure due to star formation regions, and also what is the magnetic field strength in this case, but they're more complicated to study. And the novelty is exactly that. So in the case of 1068, this is the first time that we observe large-scale magnetic fields due to polarized emission of aligned dust grains. On the case of M82, so I show here one specific wavelength, but as Fabio showed, so we need different wavelengths to show the spectrum of the emission. So we have another observation that we observed a month ago, and that will allow us to study the cold dust and the hot dust. So that if the structure is the same as hot and cold dust, then that will give us some idea on what is the dominant mechanism of polarization. But we're still working on that one. Yeah.
Okay, more questions here in the room? Oh, we have one over here.
Mike Gordon, University of Minnesota. I have a question for Fabio. You showed that the polarization spectrum correlates with density in submolecular clouds. I'm wondering if you could use the polarization spectrum also in infrared dark clouds to tell if aligned magnetic fields are either quenching or speeding up fragmentation.
Right, so let's see. I think if you're talking about fragmentation of the clouds, that's what you're talking about, right? I think for that you would need some estimate maybe of the field strength itself. The thing about the polarization spectrum is that it is very sensitive to variations in the grain alignment, because we're basically taking two different wavelengths, and in principle, the two different wavelengths, they are mapping the same magnetic field lines. So if you take the ratio between them, you're kind of canceling a few magnetic effects. For example, inclinations of magnetic field lines along the line of sight. You kind of cancel that contribution, and you are left with something that depends only on the efficiency of the alignment of the grains. Okay, so that's why the spectrum, the polarization spectrum, is interesting to look at the grains. But if you're trying to study dynamics of the cloud formation, for that I think you would need to understand the geometry of magnetic fields and also the strength of magnetic fields. And this is something that is very hard to do. There are techniques that can be used to estimate the strength of magnetic fields, but we hope that once we understand better about the grain alignment, we'll be able to estimate the field strength even better as well. So, yeah.
If I could add to that, I would say that the other great strength that Fabio's map here shows is if you look at the number of independent polarization vectors over the area, one way of addressing the fragmentation and the structure of the cloud is also to look at autocorrelation function. In other words, how well correlated are two vectors at various distances. And one of the things that HAWC is doing fantastically is that it has the resolution to get us a lot of numbers. And there are several groups both within the HAWC team and as general observers on Sofia that are looking at that thing, how far away from each other do the vectors agree, and that will tell you about fragmentation as well.
Inga, do we have any questions on the webcast? No? Any more here in the room? Okay, one down in front. Steve?
So I came in a little late, and I apologize if there were some earlier remarks I missed, but obviously Sofia is doing great. At one time, NASA was going to more or less shut it down. What are the prospects now for continued operations into the future?
And that was from a man who needs no introduction, which is why he didn't give himself one. It's Steve Marin.
I can take that, Steve. So Sofia is in its full operations period right now. We reached full operations capability in May of 2014. And we are in the process of preparing for our senior review. The senior review is a review of all NASA's operation meetings and missions. And Sofia will undergo its first senior review in 2019, a year from now. And that is for, the National Academies have done the cadence now for every 3 years. So we join the rest of NASA missions to go through the review. So we're writing that proposal to continue the operations for a 3+3 landscape. Meanwhile, the observatory is operating wonderfully right now. We introduced the new instrument HAWC Plus this past year, and also commissioned upgrades to the German instrument GREAT, which we can go in great detail, but I can tell you more about that, and posing some exciting science for this upcoming Cycle 6, which starts next month.
Any other questions here in the room? Well, I always have a few. So Fabio, you mentioned that polarization, you described it as slightly polarized. I'm just curious, sort of what level of polarization are we talking about? Are we talking about fractions of a percent or tens of percent or something like that?
That's usually a few percent. Mm-hmm. So when you look at this polarized emission from molecular clouds and diffuse clouds as well, we usually find levels, let's say between 0 and 10%, something like that. So it's a relatively small fraction of the light that is coming from those clouds that is polarized.
Mm-hmm. And then if I want to make sure I understand the two effects that you described that are creating alignment. There's radiative forces that are aligning grains, and then there's the magnetic field that's aligning grains. And if I understood the presentations correctly, the radiative effect is acting on individual grains, and then the ensemble of the grains in the cloud are being aligned similarly by the magnetic field. Is that right?
So what's going on is that the radiation makes the grain spin, and that's what's required for the grain to see the magnetic field.
Okay.
So it's always on the level of the individual grain that the alignment happens. But let me take off a little bit on your question and point out that not only is the alignment mechanism what drives the alignment, what makes it better, is something we're still working on. There's a number of other questions in interpreting the polarization magnetic field, which has to do with how many of the grains are aligned, because around the grain, no matter what you do to it, will not cause polarization, right? What's the mineralogy? Which of the grains do align? Then the grains become randomized by collisions with the gas. So there's a balance in there between making more alignment by more radiation and making less alignment by collisions. And all of these parameters need to be then put into a complete picture. And that's where it's so important to have these kind of results. as Fabio showed, where you can really nail down that is the mechanism we're seeing, and then you can go on from there.
And so related to that, the other question I had was, are you concluding that grains must be, must have a shape that allows them to be elongated based on physics of the grains and their mineralogy, or are you deducing that they must be elongated because you're seeing magnetic fields and or because you're seeing polarization and you're sure that the polarization is coming from the grains? You follow me? It's
Yes.
like, which came first?
No. I mean, so I didn't actually discuss that figure, but you can relatively easily show that the polarization has to have to do with the dust. It turns out the amount of polarization, the amount of polarization is correlated with the column density of dust through extinction or emission. The position angle of the polarization we see in the optical and in far infrared is directly correlated with that we see from synchrotron radiation. And synchrotron radiation is a physically well understood mechanism. So if you see a particular position angle of synchrotron polarization, you know what direction the magnetic field is in. Mm-hmm. So the fact that this kind of polarization correlates with the extinction tells you that's something to do with dust. And the fact that the position angle correlates with synchrotrons tells you something to do with the magnetic field. And then there's the big step to go from that more hand-waving qualitative statement to saying, okay, we are seeing this much magnetic field in these regions, right? And that black box in there is what we're trying to open up.
Mm-hmm. Okay, great. All right, well, thank you all very much. Appreciate the presentations and the fact they were so well organized and coordinated. And I thank you guys as well as Nick Veronico and Soraya Faruqi from USRA as well. I want to remind you that we have a press reception. Again, that's this evening at 6 o'clock. It's actually going to be in this room. The room will be reorganized for that. Our next press conference today is actually, or I should say our next briefing today is not really a press conference. It's a backgrounder, a seminar for science writers. It'll be at 12:45 in this room, and that's on NASA's Transiting Exoplanet Survey Satellite, where we'll get to learn about what to expect from that. And so with that, I'll say thank you. Thanks to those of you who tuned in on the webcast. And I hope to see you all here again at 12:45. Thank you very much.